Hi guys, welcome to our problem class, which is problem class 3 on energy, work and gravitation. Great, so the first problem we've got here is, it's a typical problem that's going to use some kinematics, some Newton's laws and some conservation of energy to solve a series of problems. We have a luggage slide. It's got a bit of luggage sitting on it and it's inclined at 37 degrees to the horizontal. The mass, you've got the mass of the slide there. I'll just use 10 kilograms here. And you've got the time, 2 seconds. So these are your variables that you have. From rest is another variable that you have. So the initial velocity is 0. So let's start solving the problem. You always start this thing. So the first part of the problem is asking to find the coefficient of friction between the suitcase and the slide. So we're going to have to use our kinematics that we have in the problem up there to go backwards and work out the force of friction. So it's the other way around to what we normally do. We would need to do some, in the next question, find the distance travelled along the slide and the vertical height that's lost, and then we can look at the work done by friction. Does that equal the energy loss in that in the kinetic energy plus the potential energy, the mechanical energy? And then we're going to use conservation of energy again to find out if we took the friction away, how much faster would this thing be travelling? And a couple of questions on conservative forces and non-conservative forces. Let's start with the first question A. I would start by drawing a nice diagram that says what's going on. You've got a ramp, 37 degrees in here. You've got your suitcase sitting here like this. Its mass is 10 kilograms. That is a G. Define which ways are positive. This is positive, this is the positive Y, this is positive X. So we know what our coordinates are like. Write down some of our kinematics. T equals 2 seconds. So that's after 2 seconds we're looking at. V naught is 0 meters per second, starting from rest. And V final is 1 meter per second. Okay. So that's what we have. We also should be drawing force diagrams by now, so and that's the first thing we should think of. So let's draw the total force diagram. You're going to have the normal force acting up this way. You're going to have gravity acting downwards, but we know that we can break that into its two components now, mg cos theta and another one acting this way, which is mg sine theta. And we have another force acting this way, which is the force of friction. So that's our force diagram with all the forces that are acting in the x and the y directions. We need mu k to start off with. So that's going to incorporate the frictional force and the normal force. Going to need those two things to find mu k. Another thing we can work out is we have uniform motion here. So the acceleration in the x direction is just going to be the change in the velocity over the change in time, which is Vf minus V naught divided by delta t. Put some values in for that and we get 1 minus 0 divided by 2, which is 0.5 meters per second squared. Okay, so we've already got some information about the kinematics. That acceleration is the one that links back to our Newton's laws. So that's how we're going to be able to find F, the normal force. So we're going to have to look at our force diagram and break it up into its two directions, x and y, to get a couple of equations that we can use to solve for mu k. Okay, so let's make a bit of space. So let's look in the x direction. So let's balance forces. In the x direction, let's draw a force diagram in the x direction. We're going to have F acting back this way, and we're going to have mg sine theta acting that way, and that's going to give us an acceleration ax down the plane. So that's our force diagram for the x. So we can get some equations out of that then, and we can say mg sine theta minus F, because it's in the up the plane in the negative direction, equals mass times acceleration in the x direction. That's our equation 1. Excellent. Let's have a look in the y direction. Draw our force diagram in the y direction, and we get the normal force, the plane, and we get mg cos theta acting this way. Okay, so we can write an equation. Now, they have to add to 0. They have to be equal in magnitude, otherwise the thing's going to jump off the plane. So we know that Fn equals mg cos theta. We can do a few other things here. We can say that the normal force is just the frictional force divided by mu k. That's from, the force equals mu k Fn. That's how we get our normal force, and just rearrange it for Fn. And we can plug that back into our expression here for Fn, and we'll get F equals mu k mg cos theta. Okay, that's just with a bit of algebraic manipulation. I just substituted over here for Fn, and then I, took the mu k over to this side here. So that's our second equation. Now we can substitute that back into, substitute 2 into 1. So we just take this expression and plug it back in here for f, and we get a new expression which is mg sine theta minus mu k mg cos theta equals max. Some more space. So we need to solve for mu k here, so we have to muck around with some algebra. The m's will cancel, that's nice. We'll get rid of those. So we get g sine theta minus ax equals mu k g cos theta, just by rearranging that expression. We want to get mu k by itself, so we can say mu k is equal to g sine theta minus ax all divided by g cos theta. Rearranging. We'll put some values in for that now. We have 10 times, oh sorry, we won't say 10, we'll say 9.8. 9.8 times sine of 37 minus acceleration, which we worked out earlier, right back at the start, divide by 9.8 times cos 37. And the answer I get for that is 0.69. So that's quite a large coefficient of friction. It's less than 1, so it's a coefficient. If you've got an answer greater than 1, that doesn't make much sense. Now the fact that we are a 10 kilogram block and we go from rest, and after 2 seconds we're only doing 1 meter per second, we must have a large amount of friction to do that. So that's a reasonable answer. So have a think about the answer you get before you move on, because you're going to use that in the rest of the problem. I might just switch to a new page now. No, we can just go down here. Oh no, I'll need to go to a new page. And look at the second part of the question, B, which I'll just remind you is find the distance travelled along the slide, the vertical height lost during the first 2 seconds, and use those to verify the work done by friction equals the loss in kinetic energy plus potential energy, so the loss in mechanical energy. Now, if there's no friction, there's no external dissipative force, then we shouldn't lose any mechanical energy. It should be conserved. So delta E, change in energy, should be 0. But we've got a dissipative force acting, and that is the friction. It's going to take away some energy, and we're hoping that the amount of mechanical energy that gets lost is equal to the work done by friction. That will verify this statement. Right, so let's work that out to start. To start off with, we can just draw what we're looking at. We're looking at sliding down some distance delta x down the ramp in our 2 seconds, and then we're going to drop some distance h in that direction. So this is 37 degrees. Write down some other stuff that we have. We have the final velocity was 1 meter per second. The initial velocity we know was 0 meters per second, and the time taken was 2 seconds. Okay, so it's pretty straightforward now for us to work out what delta x is, because it's just velocity equals distance over time. We use the average velocity. We can work that out this way. Delta x is equal to v naught plus Vf on 2, it's the average velocity times the time. Put some values in and we get 0 plus 1 on 2 times 2, which is 1 meter. So delta x here, in 2 seconds, we're going to go 1 meter. Great. Now it's just a trigonometry problem to find out what h is. You just use the sine of the angle there. It's going to give you your h value. It's going to be delta x sine theta, which is 1 times sine of 37, which is 0.602 meters. Those are important. We need to know delta x to work out what the displacement is in our frictional force, to work out the work done there. And we need h to work out what amount of potential energy has been lost. So that's two things that we need to now solve our energy deficit problem. So what we're looking for is the change in energy. Okay, that should be 0 if there's no friction, there's no dissipation, but we know there's friction here. So that's going to be the energy at the bottom minus the energy at the top. That's going to be our change in energy. So that's just the kinetic energy plus the potential energy at the bottom minus the kinetic energy plus the potential energy at the top. So that's half mv bottom squared, don't forget the squared term, plus mgh at the bottom minus half mv squared at the top plus mgh at the top. So some things are going to disappear here. The gravitational potential energy at the bottom is 0, so that goes away. And the kinetic energy at the top is also 0, so that goes away. And we're left with half mv squared b minus mgh t. So we can put in some values there, and we get a half times 10 times 1 squared minus 10 times 9.8 times the height at the top is 0.602 meters. And I get negative 54 joules. So our change in energy is a loss of 54 joules. We're hoping that that's the friction, the work done by friction in dissipating. So we can check that. So the work done by friction is going to be the force of friction times the displacement that we exert the force over. That's the definition of the work. So we know that the force of friction is mu k times Fn. In this case, remember Fn is mg cos theta. They balance out. And times delta x. Okay, so this guy here is just the normal force. Okay, put in some values and we get 0.69 times 10 times 9.8 times cos 37 times 1, which was the displacement. And the answer we get for that is, great, 54 joules. So the energy dissipated by friction, the work done by friction, is the energy loss, the mechanical energy loss. So that makes sense. Our answer is looking good. So the next part of the question is saying use conservation of energy to find out how fast the case would be moving if we remove friction in that situation. So we should hopefully get an answer that is greater than that answer of 1 meter per second. So that would make sense. So we need to work that out. There's a couple of questions here that we can answer very quickly. Would this answer change if the luggage slide were not straight? So if it had a curve in it like this, or if it was some weird shape. Well, because we have no dissipative forces, we're only conservative forces. Remember, it doesn't matter how we go from point A to point B. It's really only the vertical height. If we're talking about gravitational potential energy, that matters. So if we start here and we end here, it doesn't matter what we did to get to here. We're still going to have the same speed. If we put friction in, however, we dissipate some energy. That's not going to be the case because Friction is a dissipative force. It's a non-conservative force. So the situation that I just described in the first part of the question only works with conservative forces. Great. Okay, so let's go on to solve problem C, which is, work out how fast this thing would be going if there were no friction. So we can say, just using conservation of energy again, we can say the kinetic energy plus the potential energy at the top equals the kinetic energy plus the potential energy at the bottom. Okay, so half mv top squared plus mgh the top equals half mv at the bottom squared plus mgh at the bottom. And we know that that guy disappears. There's no kinetic energy at the top, starts from rest. And at the bottom, the potential energy is nothing. The m's cancel nicely, and we get gh at the top equals half vb squared. We're trying to solve for vb squared. It's quite trivial to do this now. We just get 2ght equals vb squared. Therefore, vb equals the square root of 2ght. Put in some values for that, and we get 2 times 9.8 times the height, which was 0.602, and the answer comes out to be 3.47 meters per second. So yes, that comes out to be a good answer. It's greater than 1 meter per second, and because we had a very large coefficient of friction, you know that friction is slowing that object down quite a bit. So a difference of between 1 and 3.47 with a coefficient of friction of 0.69 is probably a good answer. So think about your answer when you get it. Great. Okay, so that's that question out of the way. I'm hoping that you're getting the hang of the conservation of energy type problems. Here's another one. Now, this is a tricky question. I give it to students to make them think about these concepts of work and energy dissipation. So what you have here is a ball, and its center of mass is sitting at some height above the track here, at the bottom of the track of 0.5 meters. This is a frictionless surface except for the flat bottom just here, which is got some friction. And it rolls down, goes across this friction, hits a spring here, and then the spring returns the ball back. Now, the brute force way to solve this is quite nasty and takes a few pages of derivation to do. What students sometimes do is they work out what the potential energy of this is. They work out what its of the ball is at this point. They work out what its kinetic energy is at this point. Then they work out what its kinetic energy is after it's gone across the friction. Then they look at how far that's going to compress the spring, and then the spring will spring back and it'll go back across this and it'll lose some kinetic energy again, and it'll change its height. And then it'll just keep doing that, and they go through like 3 or 4 pages of derivation to do that. But it turns out that mgh, or the gravitational potential energy, is a conservative force. The spring's a conservative force. The only dissipative force here is the force of friction. So that frictional area has to dissipate all of the gravitational potential energy mgh of this ball. So that makes it very simple that the change in potential energy is equal to the negative of the work done by friction. Very, very simple. And we can see that it only takes a couple of lines to solve this. So then mgh is equal to F delta x. The work done by the friction, so the only place we can dissipate any of that original potential energy is across that friction surface. So we need to know how many times do we need to go across that friction surface before all the energy is dissipated. So the ball has to stop on the friction surface. It can't stop anywhere else. If it's got any velocity at any point in the non-friction surface, it's going to keep moving. So the only place it can stop at is that friction area. So we know that the friction force is mu k Fn. In this case, the normal force is just going to be mg, so it's mu k mg. So we can rewrite this as mgh equals mu k mg delta x Too easy. The mg's will cancel out on each side. And we end up with something that says delta x equals h divided by mu k. Come on. We know those values, 0.5 and 0.3, which is 1.67 meters. So we have to actually traverse 1.67 meters of that friction track before all of our energy is dissipated. Okay, so we can work out how many times that transits. So it's going to transit 1.67 divided by 0.3 times. That's going to be able to go across that friction, that amount of times, which is 5.56 times. That means it's going to go 1, 2, 3, 4, 5, and it's going to stop at some point, which is 0.56 times 0.3. So that's going to be, so it's 5 transits plus 0.56 times 0.3, which is 0.168 meters. So it's going to end up 0.16 meters, 168 meters, sorry. 168 meters from the edge of the friction. So that's a good answer. So you could have taken 3 or 4, 5 pages to derive that, or you can use conservation of energy and dissipation of dissipative and so conservative, non-conservative forces to solve it quite easily. So if I give you a question like that in the exam, and you take in 5 pages to work it out, have a think about the concept underlying the question. Okay, so this last question here, well, I've got a series of shorter questions that you can also play with. This is about gravitational potential energy. So we have a satellite, it's traveling in a highly elliptical orbit. So this is very similar to, we can look at these kind of things like in terms of Kepler's laws. You've got the Earth sitting here, you've got a little satellite whizzing around, and it's going to, at some distance r, it's going to be doing some velocity at some point out here. Now because Kepler's second law says that area at a further distance is equal to this area in a given time.
Siri not available.
In a given time, then, sorry about that, Siri interrupting my video there. Then the velocity, because this guy's traveling at this point over here, a greater distance in the same time, then the velocity here in this area here is greater. Okay, so we should find that in our answer. So we've been given some information. We've got the velocity at the far point is, where are we? It's at the far point, it is 10 to the 3 meters per second. Okay, so that's out here, it's 10 to the 3 meters per second. The distance at the far point is 5 by 10 to the 7 meters. So it's 5 by 10 to the 4 kilometers, we have to convert to meters. The velocity at the near point is what we're looking for, and the radius at the near point is given to us in the problem, and that's 10 to the 4 kilometers, so that's 10 to the 7 meters. So that's the information we have. We also have the gravitational constant, small number, because gravity is very weak, and we also have the mass of the Earth, which is quite a large number. So what we can say in this problem is the mechanical energy is conserved. So the mechanical energy of the satellite at this point, out on the far part of the orbit, is the same as it when it's at the near point. So it's being converted back and forward, but the total mechanical energy is conserved. So from conservation of energy, again, we have the kinetic energy plus the potential energy at the near point is equal to the kinetic energy plus the potential energy at the far point. This is good. So half mv near squared minus, remember it's a minus sign because gravitational potential energy has a negative sign, minus g m, little m, big M being the mass of the Earth, little m being the mass of the satellite, divided by Rn, so the radius at the near point. Okay, equals the kinetic energy at the far point, which is half mv far squared, minus g m little m over r at the far point. We can do some fun algebra here. We can get rid of the m's, little m's. The capital M's don't cancel. We can multiply through everything by 2, and we're going to get vn squared minus 2g gm over rn equals vf squared minus 2gm over rf. We just need to rearrange it. We're looking for this guy. So we can rearrange everything there to get vn squared equals vf squared minus 2gm over rf plus 2gm over rn. Still, I don't really like that algebra. I can make it neater. So vn equals the square root of vf squared plus 2gm. The gm can come out of the front, and I get 1 over rn minus 1 over rf. Okay, you can do that if you consider the signs that are going on in the last question. So I like the way that algebra looks now. I can put some values in. I go 10 to the 3 squared. Remember the squared. Plus 2 times the gravitational constant, which is 6.67 by 10 to the minus 11. Multiplied by the mass of the Earth, which is 6 by 10 to the 24. Multiplied by 1 over 10 to the 7 minus 1 over 5 by 10 to the 7. And I get a value there of 8.1 by 10 to the 3 meters per second. So our answer works out if we consider Kepler's laws, which say that at the near point we should be going faster because we're traversing a larger distance in the same time because of this equal area argument. So that answer makes sense. And this, we're told in the problem that this is a highly elliptical orbit, so we should be going quite quickly at that point. Excellent. So now we have just a couple of easy problems. These are sort of typical ones that I could give you on an exam. They only take a couple of seconds to solve. So I'm just going to quickly whiz through those. One, find the work done by the heart when it exerts a force of 4 newtons to push the blood supply of the body a distance of 20 meters. Okay, so we know the work done is force times the displacement. So the force is 4 newtons, the displacement's 20 meters. I get 80 joules. Easy. 30 seconds worth of work. Which has more kinetic energy, a 200-ton earth-moving truck at 10 meters per second or a 10-kilogram meteorite moving at 1,000 meters per second? Well, let's look at the earth mover. I'll just call it EM. The kinetic energy is half mv squared. Don't forget the squared term. That's the really important thing here. Higher velocity means it's more dependent on the velocity because of that squared term. Equals half the mass, which is 200 by 10 to the 3 times 10 squared, comes out to be 10 to the 7 joules. Okay, what about the meteorite? So the meteorite's much less massive, but its velocity is greater. So again, kinetic energy is half mv squared equals a half 10 times 1,000 squared, which equals 5 by 10 to the 6 joules. So a meteorite, 10 kilogram meteorite, imagine a little thing like that, moving 1,000 meters per second, has the same kinetic energy as a 200-ton earth mover moving at 10 meters per second. So 10 meters per second is pretty fast. It's about how fast Usain Bolt runs, or he's faster. So you can imagine a huge earth mover moving like that. That's how much energy a 10 kilogram meteorite has. So a lot of, or about half of that. That's a large amount of kinetic energy. So yeah, the earth mover has the larger kinetic energy, but it's of the same order, pretty comparable to what the meteorite is. 3, the question is saying how much work is done in increasing the speed of a 1 ton car from 10 meters per second to 20 meters per second? Well, the work done, remember, is the change in the kinetic energy. Pretty easy, which is half mv final squared minus half mv initial squared. We can neaten up the algebra there. We can say m on 2 outside of vf squared minus vi squared. Put in some values for that now. The mass was 10 to the 3, 1 ton, divided by 2. Outside of the velocities, which is 20 squared. Make sure they're in meters per second, guys, not kilometers per hour. It doesn't work out. Minus 10 squared. And that answer is 1.5 by 10 to the 5 joules, which is, order of magnitude less than that little meteorite. Question 4. Using conservation of energy, find how far a ball must fall from rest in order to achieve a 5 meter per second speed, neglecting air resistance. And it says take g to be 10 meters per second squared, but we don't do that. I'm going to assume it's 9.8 meters per second squared. I don't like using g as 10 because it's not. So we use conservation of energy. So the kinetic energy plus the potential energy final is equal to the kinetic energy plus the potential energy initially. And we can say that because there's no dissipative forces here. There's no air resistance. We've removed it. So we get half mv squared final plus mgh final equals half mv initial squared plus mgh initial. As always, we're going to be able to cancel some things out here. Final potential energy disappears, as does the initial kinetic energy. They disappear. So we get half mv squared final, v, that's a squared, equals mgh initial. The m's cancel out, and we get h initial, which is what we're looking for, is vf squared divided by 2g, which is 5 squared divided by 2 times 9.8 is 1.28 meters. Okay, so some easy problems there to get your head around. Be aware and think about these ideas of work done, dissipative, non-dissipative forces, conservative, non-conservative forces, conservation of energy to simplify problems vastly. Okay, see you next time.